So we've seen before the benefits of using tail call optimization in the place of using a linear recursion in Scheme, for example. And when our language doesn't support a looping construct, this actually becomes very important, particularly in terms of keeping runtimes from becoming explosive. Now, SWI Prolog does support tail call optimization as well. It calls it last call optimization in its documentation. So today we're going to take a look at the recursion and iteration in our Prolog programs. So let's start with the factorial problem. So if we want to solve a recursive factorial, so factorial, so actually let's do it this way first. We have n factorial, for example, is equal to n times n minus 1 times n minus 2 dot dot dot, times dot 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 times 1. And that could be described recursively instead by saying 0 factorial equals 1, and anything else, n factorial, is equal to n times n minus 1 factorial. Okay. So this is a nice recursive definition for a factorial, so let's see if we can't create a recursive code for this. So we have factorial of two values, n and f. So factorial of n equals f. For our base case, this is actually really straightforward. In fact, let's do our base case first. If somebody asks us for factorial 0, we'll give them back the value 1. Great, no troubles there. On the other hand, if we want to solve a larger value, such as factorial n, then we'll give them back some value f. But how do we calculate f? So first off, this is for all cases where n is greater than 0. In that case, then what we'll do is we'll calculate n minus 1, call factorial on that, and then just multiply the result by n. So we'll say n1 is n minus 1. Then we have factorial of n1 is, let's say, f1, sort of temporary result, the factorial of n minus 1. And then all we need to do is take that f1, multiply it by n, so f1 times n, and take this calculation and put it into this result variable f here. So we'll say f is f1 times n. And that's the recursive factorial. So we have our base case, and we have a recursive case that shrinks down towards that base case, deferring some operations. So let's consult this knowledge base. Sorry, save and consult. Recursion.pl, and ask what is the factorial of, let's say, 10. I'm sorry, factorial of 10, and we want some sort of result as our output. There you go. 10 factorial is some very large number. We can do a smaller one like 3, which is 3 times 2 times 1, which should be 6. And we get 6. Right, so that's the recursive version, linear recursive version in this case, but how could we make this an iterative solution? So there's two different ways we can do this. Let's start with the first one here. The first idea is start at 0, and we're going to keep track of a running total and a counter. Now when the counter counts up to n, then we'll just give back this running total. Okay. Now in order to do that, we're going to need some more parameters, so this problem is going to have to become indirectly recursive. So we'll have a public factorial, we'll call it factorial it underscore it of two values, n and f. But that's going to call a recursive function or an iterative function. So it'll be factorial starting with the counter at 0, upper bound of the counter is n, our running total will start at 1, and the result variable will still call f. And that's important here, that the user is going to say factorial, let's say 10. That's going to be the upper bound on our counter. But they're going to pass in a variable that's going to unify with f. So we'll say factorial of r, let's say. So r here will unify with the public f. But it's very important that the public function f here unifies with the result that comes out of our helper function as well. We should probably call this something else like factorial helper. Okay. Actually, we could call it the same thing as is standard in Prolog. The reason being we have different numbers of arguments. So we have arity2 factorial it, and then we have an arity4 factorial it. And those are very distinct rules, so there's no confusion between one to the other. So our 4-part factorial helper thing here. Let's start with the recursive case first. So the recursive case. Let's actually label this. So this is going to be the iterative factorial, and this is the public function, sure. Public predicate, as they're called in Prolog. So now we're creating this helper predicate factorial IT. So factorial needs 4 parameters here. So factorial IT. The first one is the counter. So I'm going to call it I, just a good count variable. N is our upper bound. We have our running total, so we'll call it T for total, and then our final total, which we'll call F. Okay. So all those things together need to somehow produce some information. Now notice when we're starting this iteration, we have information in some of them. We have 0 here, which is the value 0. We have 1, which again is the value 1. We have this n, which definitely has to have a value because the user wants to know what is n factorial. So we're going to assume n here has a value as well. So these first 3 terms all have a value, and then the 4th one is our result variable. So that's going to get unified with a value once we have the final answer. Okay, so first things first, this recursive case is for when our counter has not reached the end, so let's put in I is less than n, so the base case will be when they're the same. Otherwise, what we need to do is we're going to increment our counter, so I1 is I plus 1. We're going to multiply our running total, sorry, not n. We're going to multiply the current value of I into our running total. So we'll say T1, or the second version of our total so far, is T times I. Okay, so take the current value of our total, which started at 1, and multiply in each step of our counter. Oh, sorry, I probably shouldn't do that because that's going to be a 0. Let's use I1. Okay, starting at 1. Okay. And then finally, we pass all of this information into the next instance. So we'll say factorial it for I1 with n, T1, and F. Okay, so this says counter is not yet at the end. So if in that case, we'll increase the counter, we'll multiply this new value of the counter into our running total, and then step to the next iteration. Now, what happens when we get to the end of this iteration? Let's say when I is counted up to the point where it equals counter. Well, then we have our base case. Actually do this on top because base cases should come first. Just it's easier to explain recursively first. Okay, then the base case, the counter is at the max, so we're just going to return the running total. And this is going to look a little bit odd, but bear with me. Factorial IT NN FF. So what does that say? So NNFF. So what that is saying is that these two arguments are the same and these two arguments are the same. But most of these have values, right? So we saw when we started our loop that the first 3 all have values and the 4th one doesn't. So if these two have values, they have to be the same value. And if these two have to be the same, then we saw this one already doesn't have a value, the result variable. What that means is the result variable is going to collect a value from the running total. So a way to think about these return variables is they're being passed in untouched all the way through, and they're creating a chain of unification. So consider, for example, let's do with a simple factorial call. So we'll say factorial IT 3x. Let's say that was our query. Okay. What that means is, so we call factorial IT 3x. That unifies with this public predicate, where x unifies with f, and our goal then becomes this. So our goal is now that, where n is 3, and f is an unbound variable, but I'm just going to type in this a little bit differently, with x equal to f, right? Because x here unifies with f there, and f unifies with f there. So that then unifies with our, it doesn't match our base case because we have different numbers here, 0 and 3, doesn't fit this, right? So those have to be the same thing. There's no value for n that can be both 0 and 3, so that doesn't work. And it tries this one. And those are two separate variables now, so it'll work. So we'll try that then. And after a few steps, what this becomes is this recursive call, right? It verifies that I is less than n, increments the counter, multiplies our running total, and we get factorial it, incremented counter. N doesn't change, so it's always 3. And we multiply 1 times 1 to get 1. Not a big change so far. And then we call that with the variable f here. Okay. Now this f here and here in our recursive rule is different than the f inside our public predicate, so I'm going to call it f prime. Okay, so that's the f at the end of this line. But it's important to note they're united, they're linked, they've been unified. So with f equal to f prime, right? So when we said in our public predicate here, when we said call factorial it 0, 1, 0 n 1f, 0 goes into I, n matches with n, so 3 goes into n, and 1 goes into t. But then f, an unbound variable, unifies with a different f, which is also an unbound variable, by creating this unification that if one gets a value, they both do. So we have the iterative call, and that goes back to the top of our factorial again. So we get percent factorial it, and it goes through all the steps again and says, well, counter goes up by 1, n doesn't change. We say 2 times 1 to get 2, and now we have f double prime here. So this unified with the head of this, where I is 1, n is 3, t is now 1, and f, as we called it, matches a yet new instance of this variable f, which we'll call f double prime. So when that comes down to make its factorial call, it's doing so in a situation where f single prime is unified with f double prime. So again, if one of those gets a value, they both do. All right. I get one more call here, factorial it 3, 3, 6, and f triple prime. So when we called this, it unified again with the head of our rule and walked through incrementing the counter and multiplying our running variable. And the f double prime that we called here matches with this f, which is yet another instance, so we'll call it f triple prime, with again the caveat that f double prime unifies with f triple prime. Okay. Now when we call it, notice the first two values are the same. So each time, I've kind of been glossing over this, but each time it checks the base case, and because there's no single value that can make 0 and 3 or 2 and 3 the same, it's just been passing on that base case. It can't unify one variable into both of these spots. But now suddenly it can. 3 and 3 have the same value, so it can unify n as 3 in both of those spots, which is to say we now hit the base case. So our recursive call looks like the body of this base case. And technically there's not an extra step here, but it's a bit more expressive to draw it out. So factorial it, we get 3, 3, 6. And notice what this recursive case says is since this is an unbound variable, we pass in f triple prime. That will unify with f quadruple prime, I suppose. But f quadruple prime gets the same value as here. This is also f quadruple prime here. Since it's an unbound variable and we're passing in a 6, 6 unifies with an unbound variable, with that unbound variable getting that value. So it's essentially saying 6 here with f triple prime equals 6. So the specifics of the prime's not super important. The key point here is at each stage we've made a unification of an unbound variable with an unbound variable. So we passed in this unbound variable x that unified with the top level f. And then we passed in that f, which was unbound, and that unified with a new instance of f, which was also unbound. So x equals f equals f prime equals f double prime, all the way down till eventually we reach the base case where it actually got a value. So it got a value from this column here where we said unify factorial it n ff. So one value that works for n is 3, and one value that works for both of these f's, if we're unifying with this step here, is 6, right? Because we have 6 unifies with an empty variable, and empty variable unifies with an empty variable. So 6 goes into there, 6 goes into here, and now this empty variable gets the value 6, which is to say 6 goes into triple prime. But now because triple prime is equal to 6, so is double prime. And because double prime, so is single prime, all the way back until x itself gets the value 6. And that's what happens when we type in, oh, we've already typed it in here, factorial 3r in this case instead of x. R unifies with that top level variable and all the way down until we get an actual value. Okay, and that's true of all the recursive calls. It's just a lot easier to see when it's nice and iterative. All right, so that's one way we could solve the iterative factorial problem. Another way we could solve it's pretty much the same idea, but counting from n down to 0 instead of from 0 up to n. And it works pretty much the same, just it saves us an extra argument. So we could say factorial it, I'm going to call it b instead of 2. So it's the second factorial. And this works publicly the same, n comma f. So the nth factorial number is f, or the calculation of n factorial is f. So to solve this, our base case is going to be a little bit different. Still going to be indirectly recursive though, so we can say factorial. Now we do want to be careful not to step on the toes of any of our previous functions. In this case we only need 3 values. If we're counting down from f, then n itself starts as the top value of our counter, and just the constant 0, which we don't have to pass through, can be our base case. So we can actually do a factorial it, I'm going to keep it itb just to keep our names the same, but this is only a 3-argument version. So we have n is the starting value for our counter, 1 is the starting value for our running total, and f is still that result variable chain that we saw in the previous example. Okay, and then we have our base case, which works similar to previous. It's a fact, so factorial itb. We have a specific value for our counter that says it's done, and that will be 0. Now, if we've reached that base case, then we have our running total f, and we want that to match into our final total. So we'll pass the same variable in both of these parts. So if these two things have values, then this last one will get the value from the second column because it should be an unbound variable until this point, exactly as we saw in the previous example. All right, and then our recursive case, factorial itb has a counter, keep it with n, t, and f. So this is for all situations where our counter is greater than 0, so n is greater than 0. In that case, then we'll multiply the current value of n. Notice we want to multiply before subtracting because n needs to be included. So we'll say t1 is t times n, and then we subtract from our counter, so n1 is n minus 1. Okay, and then when we're finally done, we just make we take all those values, pass them to the next iteration. So factorial iterative part b to be n1 t1, and just chain the value f. So f is just passing from our inputs straight through our outputs. So eventually it gets a value here, and then that value gets returned here. So because that chain happens, this value gets it. And then that comes back through the chain multiple times until eventually it comes back to here and then back out to here, and the whole thing is done. Okay. So 2 different recursive instances. I don't think we tested either of them, so let's do that now. Recursion. So let's do factorial it. Let's just do, let's test 3x. There we go, we get 6 that way. We can backtrack, but it's going to say false. So backtrack again is when it lands on this base case. There's still the potential that it could have satisfied that last step by using this rule. So it gives us the option, but if we try, that rule has protections to prevent it from running. Okay, and we could try factorial itb, should give us the same answer. 3 times 2 times 1, which again is 6. So notice that both of these iterative functions have the same pattern as in Scheme. We have tail recursion, so the last thing the function's doing is essentially calling itself, if we're calling them functions and function calls. Essentially the last thing the resolution algorithm has to do is unify this last clause with the head of the same rule. Okay. We have a running total and a counter, so we have a counter counting up in this case, or a counter counting down in this case, but we have that counter being passed through. We have our running total that starts off at a default value, gets multiplied through at each case, and that's our final total in the end. And then in all of these, we needed a helper function because we needed extra variables. So it's very similar to Scheme, and in fact, a lot of the Scheme knowledge that we picked up through the semester is going to be really useful from here on out in Prolog as well. So let's actually follow that notion and create an iterative version of Fibonacci. So we saw the Fibonacci sequence, or the Fibonacci code here at least, in a branching recursive style, but we've seen before in Scheme how to solve this in an iterative style. So in iterative style, we have to keep track of the two previous values, starting with 0 and 1. We'll add those together to make fib of 2, and then we'll add fib of 1 and fib of 2 together to get fib of 3, keeping a counter until we get to the n that we want. At that point, we can return the running total without having to do any branching recursion. We can iteratively work forwards from the first two values to get to the nth value. So let's create a fibit. Fibit of n is r. Now again, with these iterative problems, we're going to need some extra variables, specifically a running total and a counter. In this case, we're going to need two running totals, the two previous values. We're going to need the fib of n minus 1 and fib of n minus 2. So fibit here becomes fibit n, our counter, our two running totals, 1 and 0, and r, our final result. So this is fib of n minus 1, this is fib of n minus 2. Our counter really ought to start ahead by 1 here. No, I think that's correct. Okay. All right. Off by 1 cases always end up taking me an extra step, but my notes say this is correct, so let's trust my notes. All right. So the next step for fibit is to create the base case here. So again, with an iterative approach, the base case is we've done all of the work. We have our temporary variable, has all of that information in it. We just need to move that temporary variable into our final variable slot. So in this case, the recursion stops when n, if we're counting down in this case, when n reaches 1. So we have one of our base cases. At that point, we can just return take our running total, which will be in this slot, and put it into the last slot, our final total there. So the idea being these are the Fibonacci of the two previous values. So when we make this last call, this will be the final Fibonacci number that we need, and we'll just put that into this this empty variable that we've chained through till the end here. All right, so now our recursive case, we have our counter n, we have our fib of n minus 1, so I'm going to say fib n1, and we have our fib of n minus 2, so fib n2, and our overall result, which again is just this empty variable that's being passed through. Okay, so our recursive case is for all situations greater than 1, and n is going to be counting down, so our new value for n is going to be n minus 1. And as we're counting down n, we're going to be combining the two previous n's. So these started as 1 and 0, being the fib of 1 and the fib of 0. So if we add those two together, we get the fib of 2. So we could say fib of n is fib of n1 plus fib of n2. Okay, so for the first iteration through, fib of n is now the value 2. So then we just keep going through this way. It might be a bit easier to conceive of if we count up instead. I just like using fewer variables by counting down. The edge cases can be worked out to be the same either way. All right, so we've added the first two values together to get the third value, and now all we need to do is pass all of this information into the next iteration. So we say fibit. We have our new value for the counter, so that's n1. Now our new value for fib of n minus 1 on the next iteration will be the current value of fib n, so fib n. The next iteration will count fib 3, and that's going to be fib 2 plus fib 1. Notice we don't need fib 0 to calculate fib 3, so we can throw that away. So we take fib 2 as the fib of n minus 1. We'll take fib 1 as the fib of n minus 2. So the new fib of n minus 1 is the old fib n. The new fib of n minus 2 is the old n minus 1. Oop. And then, as always, we just pass through this empty variable that's not going to get used until that very last step, but it has to be there to create this chain of combinations, this chain of unifications, so that eventually this last value can make it back to the surface and unify with the query variable that we started with. But that's pretty much everything there. So let's test this out. So we have our starting value, 1 and 0. Those get added to get 2, and we pass in 2 and 1. And those come back around. We add in 2 and 1 to get 3, and then we pass in 3 and 2. Those get added together to get 5. We pass in 5 and 3. Added together to get 8, etc., etc. Fibonacci sequence. All right, recursion. Reconsult this knowledge base, and let's run it. So how about fibit 5 is x. And that's 5, that's great. And then we want the next value, so 6 should be 5 plus 3 is 8. Great. And 5 plus 8 for the next one should be 13. That seems to be working. Okay, so that's the idea behind the Fibonacci sequence. So again, we're counting things down. So here, I'll just do a quick substitution model, so to speak, again. If we said fib of 5 is x, then we end up with fibit 5 is our n, with the first two values 1, 0, and this result variable that doesn't change. And then that comes down to n minus 1 is 4. We pass in 0 plus 1 is 1, and then we shift the first one down over, and we have this r variable again, which doesn't change. And again, fibit, n shrinks down again, so 3. We add those two together to get 2, and shift 1 over to get 1. And then we try again, fibit 2. So we're just counting down that first column. So remember, this is the counter, n minus 1, n minus 2, and the result. So we add those two together, 3, shift the 2 over, and r stays the same. And last one, I think, fibit 1. We add those together to get 5, which is the answer for fib of 5. We shift that 3 down. We don't actually need that in the end now. And r. And now notice this matches our base case because we have 1, we have an empty variable, and an empty variable here. So 1 will unify with 1, r will unify with 5, which means this empty variable r will unify with this r prime, let's call it, which has the value 5 now. And notice we didn't need this extra value here, so underscore variable. Okay. Which in the end means that r gets the value 5. That goes right up this whole chain. These all become 5s, and then this final x becomes 5 as well. All right, so that's iteration. Again, it works a lot like scheme, so dust off your notes from scheme iteration. Make sure you understand that as well. Future lectures, we'll take a look at lists in Prolog, which again work a lot like schemes. So if you paid attention to the first half, of course, the second half should be a breeze. And I'll talk to you in the next video.